Explanation: a line integral adds up a quantity along a curve, just as a hiker adds up the elevation gain while walking a trail. There are two kinds: Scalar line integral integrates a scalar field f of x, y, z over a curve c, weighting each tiny piece of the curve by its length. Mathematically, integral over c of f ds equals integral from a to b of f of r of t times the norm of r prime of t dt, where r of t parametrizes c and ds is an infinitesimal arc length. Real-world example: f could be temperature. The integral gives the total heat experienced while walking along a pipe. Vector line integral, also called work integral, integrates the dot product of a vector field f with the tangent of the curve, giving the work done by a force field when moving a particle along c. Integral over c of f dot doctor equals integral from a to b of f of r of t dot r prime of t dt. Analogy: pushing a sled along a winding road. Each push is f dot doctor. Example question: evaluate integral over c of open parenthesis x squared plus y close parenthesis ds, where c is the circle x squared plus y squared equals 4 traversed once counterclockwise. The solution uses the parametrization r of t equals open parenthesis 2 cosine t comma 2 sine t close parenthesis, t from 0 to 2 pi, computes f equals 4 cosine squared t plus 2 sine t, and norm of r prime equals 2, then integrates. To evaluate a line integral, we first write the curve with a parameter t. Think of the curve as a movie reel. Each frame t shows a point r of t. The differential dr becomes r prime of t dt, and the arc length element ds equals the norm of r prime of t times dt. Sample problem: compute the work done by f of xy equals open parenthesis y comma negative x close parenthesis on a particle moving along the straight line from 1 0 to 0 1. 1. Parametrize the line r of t equals open parenthesis 1 minus t comma t close parenthesis 0 less than or equal to t less than or equal to 1. 2. Find r prime of t equals open parenthesis negative 1 comma 1 close parenthesis. 3. Evaluate f of r of t equals open parenthesis t comma negative open parenthesis 1 minus t close parenthesis equals open parenthesis t comma t minus 1 close parenthesis. 4. Compute the dot product f dot r prime equals open parenthesis t close parenthesis times negative 1 plus open parenthesis t minus 1 close parenthesis times 1 equals negative t plus t minus 1 equals negative 1. 5. Integrate integral from 0 to 1 of negative 1 dt equals negative 1. The negative sign tells us the force opposes the motion, and the magnitude 1 is the total work. This method works for any curve, whether straight, circular, or highly twisted. The key is a clean parametrization. The fundamental theorem for line integrals says that if a vector field f is the gradient of some scalar potential phi, that is, f equals nabla phi, then the line integral depends only on the start and end points, not on the path taken. It is the multi-dimensional version of the elementary theorem integral from a to b of f prime of x dx equals f of b minus f of a. Path independence is analogous to walking on a perfectly flat ground. No matter which route you choose, the change in altitude, also called potential, is the same. Exam type question: let f of x comma y equal the ordered pair open parenthesis 2xy close parenthesis comma open parenthesis x squared close parenthesis. Show that f is conservative, find a potential phi, and evaluate the line integral of f dot doctor, where c goes from the point 0, 0 to the point 1, 2 along any curve. Solution outline. Step 1. Check the curl in 2 dimensions. The partial derivative of 2xy with respect to y is 2x, and the partial derivative of x squared with respect to x is also 2x. They are equal, so f is conservative. Step 2. Find phi by integrating the partial derivative of phi with respect to x equal to 2xy. Integrating gives phi equals x squared y plus g of y. Step 3. Differentiate phi with respect to y. The partial derivative of phi with respect to y is x squared plus g prime of y, which must equal x squared. Hence g prime of y equals 0, so g is a constant, which we can set to 0. Step 4. The potential is phi of x comma y equals x squared y. Step 5. Evaluate phi at 1, 2 minus phi at 0, 0. That is 1 squared times 2 minus 0, which equals 2. Thus, any path gives the same answer too. This theorem is powerful for simplifying work or energy calculations in physics and engineering. Explanation: a surface integral of a scalar function f of x, y, z adds up the value of f over a surface S, similar to painting a curved wall and measuring the total amount of paint used. The infinitesimal area element on a parametrized surface R of u, v is ds equals the magnitude of r sub u cross r sub v times du dv. Example computation. Compute the surface integral of z ds over s, where s is the part of the paraboloid z equals 4 minus x squared minus y squared that lies above the xy plane. What's debs? Step 1. Choose a convenient parametrization using polar coordinates. X equals r cos theta, y equals r sin theta, z equals 4 minus r squared, with r ranging from 0 to 2 since z greater than or equal to 0 implies r squared less than or equal to 4, and theta ranging from 0 to 2 pi. Step 2. Write r of r comma theta equals the vector r cos theta, r sin theta, 4 minus r squared. Step 3. Compute partial derivatives. R sub r equals cos theta, sin theta, negative 2r r sub theta equals negative r sin theta, r cos theta 0. Step 4. Cross product magnitude. The magnitude of r sub r cross r sub theta equals the square root of negative 2r times r cos theta squared plus negative 2r times r sin theta squared plus r squared, which simplifies to r times the square root of 4r squared plus 1. Step 5. The integrand becomes z ds equals parentheses 4 minus r squared close parentheses times r times the square root of 4r squared plus 1 times Dr. d theta. Step 6. Integrate. The double integral from theta equals 0 to 2 pi and from r equals 0 to 2 of parentheses 4 minus r squared close parentheses times r times the square root of 4r squared plus 1 Dr. d theta. Perform the inner integral using the substitution u equals 4r squared plus 1 and multiply by 2 pi. The final numeric value evaluates to approximately 84.8 units of whatever f measures. This process shows how the geometry of the surface enters through the Jacobian, the magnitude of r sub u cross r sub v. The surface integral of a vector field f over a surface S gives the flux, the amount of field that passes through the surface, like water flowing through a net. Double integral over S of f dot n d s equals double integral over d of f of r of u comma v dotted with r sub u cross r sub v du dv, where n is the unit normal direction of flow, and r sub u cross r sub v gives the oriented area vector. Sample question with the divergence theorem. Let f equals the vector open parenthesis x comma y comma z close parenthesis. Find the outward flux across the closed surface of the unit sphere x squared plus y squared plus z squared equals 1. Solution using divergence theorem. First, compute divergence. Nabla.f equals partial x with respect to x plus partial y with respect to y plus partial z with respect to z equals 3. The theorem states that the surface integral of f dot n ds equals the volume integral over v of nabla.f dv, where v is the volume inside the sphere. The volume of a unit sphere is 4/3 pi. Multiplied by divergence 3 times 4/3 pi equals 4 pi. Thus the total outward flux is 4 pi. The same result can be obtained by directly parametrizing the sphere. R equals open parenthesis sin phi cos theta, sin phi sin theta, cos phi close parenthesis and integrating, but the divergence theorem makes it trivial. This illustrates how flux problems in engineering, for example heat flow through a shell, are often simplified by converting a surface integral into a volume integral. Explanation: volume integrals add up a quantity over a three-dimensional region. The choice of coordinates should match the shape of the region, just as you pick a ruler that fits the object you are measuring. Cartesian xyz is best for boxes, cylindrical r theta z fits pipes, spherical rho theta phi suits balls. The differential volume elements are Cartesian dv equals dx dy dz, cylindrical dv equals r dr d theta dz, spherical dv equals rho squared sin phi d rho d theta d phi. Example problem. Compute triple integral over e of x squared plus y squared dv, where e is the solid cylinder defined by x squared plus y squared less than or equal to 4 and 0, less than or equal to z less than or equal to 5. Solution using cylindrical coordinates. Step 1. Substitute x squared plus y squared equals r squared. The region: 0 less than or equal to r less than or equal to 2, 0 less than or equal to theta less than or equal to 2 pi, 0 less than or equal to z less than or equal to 5. Step 2. Integral becomes integral from 0 to 5 of integral from 0 to 2 pi of integral from 0 to 2 of r squared times r d theta dz equals integral from 0 to 5 of integral from 0 to 2 pi of integral from 0 to 2 of r cubed d theta dz. Step 3. Integrate in order. Integral from 0 to 2 of r cubed dr equals 1/4 r to the 4th, evaluated from 0 to 2, equals 1/4 of 16 equals 4. Then integral from 0 to 2 pi of 4 d theta equals 8 pi. Finally, integral from 0 to 5 of 8 pi dz equals 40 pi. Thus the volume integral equals 40 pi. If the region were a sphere, switching to spherical coordinates would simplify the limits drastically. The key skill is recognizing the geometry, choosing the coordinate system, and remembering the Jacobian factor r or rho squared sin phi. Explanation: Gauss's divergence theorem converts a flux integral over a closed surface into a volume integral of the divergence of the field inside. It is the three-dimensional analog of the fundamental theorem for line integrals. Statement: for a vector field f bold with continuous partial derivatives on a region V bounded by a closed surface S oriented outward. Double integral over S of f bold dot n ds equals triple integral over V of nabla dot f bold dv. Physical analogy: imagine a balloon S filled with air that is expanding. The net air leaving the balloon flux equals the total rate of expansion inside divergence. Important exam question: let f bold equal parentheses yz, xz, xy close parenthesis. Find the outward flux across the surface of the cube that lies in the first octant with vertices at 0, 0, 0, and 1, 1, 1. Solution steps: Step 1: compute divergence: nabla dot f bold equals partial derivative with respect to x of parentheses yz close parenthesis plus partial derivative with respect to y of parentheses xz close parenthesis plus partial derivative with respect to z of parentheses xy close parenthesis equals 0 plus 0 plus 0 equals 0. Step 2: since divergence is 0, the volume integral over the cube is 0, hence the total outward flux is 0. Step 3: optional check: compute each face's contribution. They cancel, confirming the theorem. Why useful: without the theorem you would need to evaluate 6 separate surface integrals. With it, the answer drops to a single volume integral, often trivial. In engineering, the theorem underlies continuity equations for fluid flow and Gauss's law for electric fields. Stokes's theorem links a surface integral of the curl of a vector field to a line integral around the boundary of that surface. It generalizes Green's theorem from the plane to 3 dimensions. Statement: for a smooth-oriented surface S with positively oriented boundary curve C. The line integral around C of f dot dr equals the double integral over S of nabla cross f dot n ds. Analogy: think of a whirlpool curl in a pond. The total rotation measured over a patch of water equals the net circulation you would feel walking around the edge of that patch. Representative exam question: let f equal vector open parenthesis negative y, x, 0 close parenthesis. Evaluate the line integral around C of f dot dr where C is the circle of radius 3 in the xy plane oriented counterclockwise. A solution using Stokes. Step 1: compute the curl. Nabla cross f equals vector 0, 0, partial derivative of x with respect to x minus partial derivative of negative y with respect to y, which is 1 plus 1, giving the vector 0, 0, 2. Step 2: choose S as the disk bounded by C. The unit normal n is k upward. Step 3: surface integral. The double integral over S of the dot product of vectors 0, 0, 2 and 0, 0, 1 ds equals 2 times the double integral over S of ds, which is 2 times the area of the disk. Step 4: the area of the disk equals pi times r squared, which is pi times 9, giving 9 pi. Step 5: the result is 2 times 9 pi, which equals 18 pi. Thus, the line integral equals 18 pi. Stokes's theorem is indispensable for converting difficult line integrals into easier surface integrals or vice versa, and appears in electromagnetics, Faraday's law, and fluid dynamics circulation.